for this loop.
Okay. So, this. Hello? This works, okay. So can I start or should I wait?
Yeah.
Okay, so I can start. Okay, so today I will give a small introduction to graph signal processing and its applications. So for those who don't really know me yet, I will first introduce myself, as most people do. So I'm from Sweden, in Northern Europe, so from a small town called Borås. So currently I've been working as an engineer at PFN for about 6 months, but I've been in Japan for about 4.5 years. Not consecutively, I guess, but I first started in 2011, since I took part in an student exchange program at Tokyo Tech. My main research interests now, things that I find fascinating, are computer vision and various types of deep or graph-based machine learning, basically. So my experience so far is that I have bachelor and master in software engineering and computer science from Chalmers University of Technology in Sweden. And then I came back after my student exchange program here to Japan to do a PhD at Tokyo Tech. I just finished last year. So some professional experience so far is that in Sweden I've been working on various more shorter time software development jobs. I worked on developing some kind of vehicle AI simulation system and also face recognition algorithms for mobile platforms. And then in Japan, I also did some server maintenance by being research assistant. And I was also an intern at the Rakuten Institute of Technology, where I also worked with computer vision. And so now I'm an engineer at PFN, and this is sort of my first full-time job, but maybe it's the last one, or I don't know. I have to see how long I'm here. So I have some publications so far, some peer-reviewed conference papers and journals from various countries. I have a few open source projects on GitHub. One method that's called pipeline grid search. It's something I developed for speeding up grid search in the scikit-learn library. And also a library for calculating matrix gradients. And another thing which I did while working here at PFN is open sourcing a chain implementation of a graph CNN paper that was published in NIPS last year. And this is sort of related to what I will be talking about today. So I guess I should talk something about hobbies and some random info. I think the main interest why I wanted to come to Japan in the first place was because I saw Japanese culture through anime. And some of my favorite animes, I guess, are School Rumble, GTO, and Kyoani stuff. I'm not sure if you have seen them before. And otherwise, I really like watching movies. One of my favorite directors is Quentin Tarantino. Like his classics, Pulp Fiction and Kill Bill, for example. Kill Bill also features some kind of pseudo-Japan scenario, I guess. I like doing skiing, snowboarding quite a lot recently. I think Japan is really great for that. I went out 5 times this season. And like food-wise, I really like spicy food. So if you know any good, very spicy food around here, so let's go lunch or something. And one of the best things about being in Japan, I think, is that we have onsens here. Yeah, I think it's really a nice combination to be out in the nature in Japan and walk a bit, and then finally, when you're really tired, after maybe climbing a mountain, you can go to an onsen. That's really nice. You don't have too many countries where you can actually do that, so it's something to be really proud of, that you have onsens in Japan. And I also like reading about popular science, just more like light reading. For example, like mathematical history. I really like the history behind the Fermat's last theorem, for example. It's a very interesting development. So I guess that's about the self-introduction, I guess. So today's seminar will be about the field of graph signal processing and what we can apply it to. And I'm sort of assuming that you have a basic understanding of classical signal processing. Like, how many knows what a Fourier transform is? Okay, so okay, maybe half of the people. I see. So maybe it's not too important to understand all the details, but like the main purpose of this talk is to try to convey what graph signal processing is, what problems we have, what can it be used for, and what kind of interesting research can be done from now on in this field. So let me start by motivating why it's interesting to process signals on graphs. So one thing is that if you really think about it, graphs are really existing everywhere. And I think graphs are really beautiful in a sense because they can capture complex relational characteristics, such as spatial or topological ones. So in computer graphics, for example, if you have a model of a human body, like here, you can represent it using a graph by modeling it as a 3D mesh. And also, of course, if you have some kind of wireless sensor networks, you can create a graph to represent that, and even an image can be represented as a graph. In an image, you can take neighboring pixels and connect them with edges to create a model of how the image looks like. So one example of what you can do with graph signal processing is citation network analysis. So in this graph here, we have it describes a set of research papers actually. So each vertex is a research paper, and if one paper cites the another paper, you add an edge between them. And each vertex has a feature vector that describes this paper using some kind of embedding. And by using graph signal processing techniques, you can sort of cluster these this network of papers and try to find out what types of papers there are. Might be that the yellow ones correspond to biology and blue is computer science, so like you can find out this automatically. Another example I think is interesting is that you can use graphs for computer vision. One is for the problem of correspondence. So I mean, classically in computer vision, we describe the object using an image, but that's maybe not the most appropriate medium for describing the object. Because even if you see you have 3 different persons who have quite different body shape, like more thin or flatter type of body, then you still want to model like what is this blue point here corresponding to it in this other body. If you just use an image, you have the problem that well, due to different body shape, it actually looks quite different. But if you instead model all of these body shapes using a graph, then the essential intrinsic structure of the bodies will be the same, like no matter how much you expand or make the body shape thinner. And you can also use graph signal processing for similarity tasks, which is sort of the opposite of correspondence. So while in correspondence you have different types of shaped parts that are actually the same ground truth part of the body, in similarity you have the same part like the face here, but you want to distinguish them because maybe the facial expression is different. So if you construct your graph in a different way, you can also take advantage of the local connectivity that describes the face to distinguish if somebody's angry or happy, for example. So basically, the way you use graphs in computer vision is that like the main idea is that a graph is able to represent a manifold. So a manifold is something that describes the local surface of a geometric object. So we have this Swiss roll here. I mean, the Swiss roll is not, it doesn't lie in Euclidean space. It's just like the Earth here, that the shortest distance between 2 points on Earth is not a straight line. But if you're this ant that's walking on that manifold, and this ant is only able to see in a very short distance around it, it actually seems that the space it's walking on is Euclidean. So you can use the graph to represent this idea that if you only look at the local neighborhood of a point, then that array actually behaves in a Euclidean manner. So what you would do is that you, on this manifold, you look at a certain point and then look at the tangent space around it and connect very locally nearby points with edges. And this creates a graph that represents the whole object. So if you assume that you can represent a geometric object using a graph, then we can also define some kind of signal on this graph and use these signals to analyze the graph and actually see what makes it different or more similar to another type of graph. So we assume in this framework, I will discuss this, that we have a graph that is a set of vertices and edges, and also a weight matrix, W, that represents the weight between two vertices. And necessarily in this framework, we need to assume that the graph is undirected. And if you, in such a graph, we can define a vertex signal that's expressed through a function g that maps each vertex to just a scalar number. And then the graph signal in this graph signal processing framework is just a vector of all the possible vertex signals defined on this graph. So that's sort of what a graph signal is. So an example here is on the Peterson graph, which is quite a famous graph in the graph community. At each vertex, you have this blue bar, which represents basically the scalar value of the signal. And each vertex is connected to another, and you can take advantage of this to understand how the signal varies, for example. So let me move on to the graph Fourier transform. So I asked if you know what the Fourier transform is. This is, in most universities, you learn this in your undergraduate studies, but basically, if you have in classical signal processing, if you have a function that's defined on a real line, you can do the Fourier transform to expand this function in terms of complex exponentials. So basically what it does is that you have some kind of function and you do the Fourier transform, so then you can analyze how much high frequency parts do you have in this function or how much low frequency parts of it exists in this function. So it allows you to understand if your function is behaving smoothly or if it's very widely high frequent or like that. So this is the classical Fourier transform, and it also has a discrete extension if the function is not defined on the real line. You might also know that there is a fast Fourier transform that is very efficient for calculating this. So what does this Fourier transform have to do with graphs? So to understand the connection with graphs, I want to consider an example of a ring graph. So it looks a bit like the Chainer logo, maybe, but but it's just a graph that's, well, it's a circular graph, and each node has degree 2. So degree means the sum of the edges that each node has. So we can represent this graph using the weight matrix W, which I talked about before. So it just means that the vertex at row I here is connected to the vertex at the second row here is connected to the second one with weight 1, and so on. And the degree matrix is just a diagonal matrix, D here, which describes the degree that each vertex has. So given just these two matrices, we can create the matrix L here, which is called the graph Laplacian matrix. The interesting connection between the Fourier transform and graphs is that if you calculate the eigenvectors of this matrix L, they become exactly the exponentials that are used in the Fourier transform. This e to the power of -2 and so on. So you can represent the classical Fourier transform on a signal that's represented as a circular graph, basically. So as an extension of this idea, so what happens if the graph is not a ring graph, but just any type of graph? This will lead us to the idea of the graph Fourier transform, where you have a set of eigenvalues and eigenvectors of the graph ablation matrix. So the smallest one is 0, and then they are increasing. Maybe you don't need to understand all the details about this equation here, but basically it's very similar to the Fourier transform in terms that you have a function g that's defined on the vertices of the graph. And instead of the complex exponentials that I talked about in the Fourier transform, you use the eigenvectors u of the graph ablation matrix to create a graph Fourier transform function g hat, which describes the frequency of this function that's defined on the graph. So you will know for this graph function, like how much of high frequency information does it contain, or how much low frequency information, for example. It also has an inverse. So in classical signal processing, we have this interpretation of frequency. For graph signal processing, there's also an interpretation of frequency, and it turns out that there's a quite interesting connection here that the first eigenvalue is always 0, so this corresponds to the DC component in classical signal processing. So this is basically the part of the signal that's always constant, that doesn't fluctuate anything. The other eigenvalues of the graph ablation matrix, they represent some kind of frequency. So if the eigenvalue lambda L is quite low, very small, then if you use the corresponding eigenvector UL here, you'll get an association that represents low frequencies in the graph signal, and vice versa, the more higher lambda gives a higher frequency. So each eigenvector has sort of a different meaning on this graph frequency spectrum. And, one interesting thing about this eigenvector here is that if lambda is quite low, then two components of this eigenvector ui are quite similar to each other. But if it's high, then they're very different from each other. This is, rather than showing a map, it's probably easier to look at this figure here. So here is some random sensor graph with a graph with some signal on it. And so U0 here is the DC component, the eigenvector that corresponds to no fluctuation at all. So what this graph represents here is that for each vertex, the blue bar represents a positive value, and the black ones represent a negative value. So you can see that the first eigenvector has only blue positive values of the same scalar value, basically. So it doesn't. If you use U0 in this Fourier transform, so U0, then it will not cause, it will not do any addition or subtraction of the neighboring elements of G here. But on the other hand, if you look at U1 or U50, you see that it becomes much more violently fluctuating. So U50, you have a lot of nearby vertices. They have actually opposite signs. So in effect, when you do the graph Fourier transform, the resulting effect is that the signal on neighboring vertices will be subtracted from each other. So you'll sort of model the difference between neighboring vertices. So, and I also wanted to mention we can measure the number of zero crossings in this graph. So it's just for each connected vertices. So this is the set of edges. So for all edges, if you look at the the value of the eigenvector at the ith vertex and the jth vertex, and if this multiplication is smaller than 0, then it actually means that they have opposite signs, right? So you can see that if you plot the value of lambda versus the number of zero crossings, you can see that the eigenvectors, they will have a lot more zero crossings when the lambda increases. So this justifies why the eigenvalues carry like a frequency interpretation. Basically, just like in classical signal processing, in graph signal processing you have two domains. So a graph signal can be represented either as a signal in the vertex domain, which is like what you originally model your problem in. So the vertex domain could be, so let's say if you use a graph to represent an image where you connect nearby vertices by edges, then the signal here could be the grayscale value of each pixel. But whereas if you take the graph Fourier transform, then you will get information, you will represent this signal in the graph spectral domain, which then gives information about how much in the image you have, well, edges, for example, if you have sharp discontinuities in the image. And for just creating equivalents, like if you want to do filtering or create a convolution, like in deep learning, we also have convolutions are quite popular, right? So you can define some kind of filter that represents a convolution, let's say, directly in the graph spectral domain, and then transform it back to the vertex domain to apply it to analyze the signal. Yeah, so it's basically just remember that we have two domains, vertex and the graph spectral domain. I briefly would just want to give you some idea of what kind of operators exist in graph signal processing, because if you just think that it's easy to translate all the classical signal processing operators to graphs, you will encounter some kind of certain issues. One is translation. So if you have a classical signal, if you know the signal at time t, you can also measure it 3 seconds back, perhaps. That's quite easy. But if you just have an arbitrary graph, how do you select the third previous vertex? This is not well defined, because from one vertex, you don't really know what does it mean to jump 3 vertices back in a graph. The ordering is pretty much arbitrary in a graph. So this is an issue. Modulation is another operator we have in graphs in signal processing, which basically means that you can shift the frequency of a signal by multiplying the function by just an exponential. But so this works in classical signal processing because the frequency spectrum is continuous. But in graph signal processing, the eigenvalues that represents the frequency, they are not continuous. They're discrete, so you'll get another type of problem there. And another problem is downsampling. So we do this in deep learning also. We have a large image, and then we do strided convolution, for example, and it becomes half the size. But if you just have an arbitrary graph, what does this really mean? So on an image, this is quite easy because you can just remove every other vertex or take the average of them to create a new, smaller graph. But if you have an arbitrary graph, how do you make this graph half the size so that it actually captures the properties of the original graph? That's another problem. So I just want to give you some examples of what can be done in graph signal processing with regards to operators. So maybe understanding the details here is not the important thing, but just understanding what can be done. So in classical signal processing, for those who know that, you can do filtering a signal by basically taking the Fourier transform of the signal and then multiplying it in the Fourier domain. You can do the same thing in graph signal processing, so that's not an issue. You just need to find some kind of filter that's called a chat. It can be, for example, like a low-pass filter, so it smooths the signal. It corresponds to a Gaussian smoothing, for example. You can also actually do filtering directly in the vertex domain by just looking at a vertex and all its neighbors, and then just taking maybe the result of the filtering to be the average of all its neighboring vertices. And you don't necessarily have to do just the immediate neighbors, but you can do a random walk in a graph, or use the whole neighborhood that you can achieve in k hops from the center vertex. So this is a bit similar to what we do in deep learning, because even though you can, I mean, in theory, it's more efficient in deep learning to take the Fourier transform of the signal, then apply the convolution filter in the Fourier domain, and then take the inverse transform back. But we don't actually do that because on a GPU it's more efficient to just apply convolution as a sliding window. Take the element-wise multiplication and sum. So with regards to that, this vertex domain filtering for graphs is a bit more similar to what we do in deep learning, in practice at least. So just an example of how filtering on a graph works, and to show the power of it. So if you have an original image of this cameraman here, and then apply some noise to it, and then we want to compare the standard Gaussian filter for smoothing this image with different standard deviations. So these two here are Gaussian smooth filters, and the last third one here is filtered using a graph. So the difference here is that the Gaussian filter is only able to look at information that's vertical or horizontal in the image, but we can create this graph to capture arbitrary connections between pixels. So in this example, the graph is constructed so that around each pixel you connect not only the left and right and upper and top one, upper and bottom one, but you also connect diagonally, so you get information from the diagonally adjacent pixels. And this is shown to actually create a much better denoising of the image. So one operator that's very interesting for the deep learning community is convolution. So I'm sure most people are familiar with convolution since it's used for deep learning, right? This is the classical definition, but if you want to generalize this to graphs, we face a problem. It's due to this term t minus tau. So h is generally our convolutional filter that this is learned by deep learning, right? And you transfer this around on the signal to create the result of the convolution. But as I said before, you don't really, if you have a signal on a graph, you don't really know what does it mean to move to like tau steps from the current vertex. It's not well defined. So you cannot apply this directly. However, there is a way around it, because in classical signal processing, there is this interesting theorem that says that the convolution in the signal domain is equal to just taking the Fourier transform of both the convolutional filter and the actual signal, and then multiplying them in the spectral domain. And this applies for graphs as well. So we cannot define the convolution operator directly on a graph, but we can do this in the graph spectral domain. So the actual convolutional filter is represented using this h hat, which means that we need to learn the weights for a convolution in the graph spectral domain and not in the vertex domain. So this is that's like a point that's different for classical deep learning convolutions, for example. Translation, it's the similar issue, right? You can move 3 steps back. But there's an interesting way to go around it, because if you can view translation as doing just a convolution with a filter that has the signal 1 at only one point and it's 0 everywhere else. So this will efficiently just move this original signal to be centered around whatever vertex had this unit 1 signal. So maybe the details are actually not so important, but just remember that translation cannot be directly used, but we also circumvent this by operating in the graph spectral domain instead. So just a few examples of translating on a graph. So here we have a graph that represents the state of Minnesota. I think each vertex is a city, I think. And the edges correspond to the amount of traffic that's flowing between each city. So if you have a signal defined around a certain city, you can translate it to another part using this delta 1 unit convolution to find out what happens in other cities as well. Maybe I should talk a bit about modulation. So modulation in classical signal processing is the operation of shifting the frequency. You can do this by multiplying an exponential to the original function. And so basically this translates quite nicely to graph signal processing because you can use the eigenvectors of the graph translation matrix. So this, you just need to remember ui, here is the eigenvector, and multiply it by the original function. So this is, it's not exactly a translation in the graph spectral domain because the graph spectral domain is still discrete. So you cannot enforce that it will translate in to exactly a certain amount of frequencies. But there is still some localization. Dilation is another operator, which is basically the way of scaling a signal for classical signal processing. So the problem here is that you have the signal at t, and you want to scale it by some scalar s. What we do in graph signal processing is that we represent the position of each vertex using an integer. So if t divided by s is not an integer, then you cannot generalize this directly. But instead, you again move to the Fourier domain and just multiply the frequency by the scalar s instead. And that's essentially what you do in graph signal processing as well. So a lot of the generalization for classical signal processing that deep learning is based on, you cannot do that in the classical signal domain, but you need to work with the spectral frequencies instead. So this whole framework is based on a lot of the spectral graph theory. And finally, just want to mention about coarsening or downsampling a graph. So there are certain problems here. So like I said, for an image, you can easily downsample it by just removing every other vertex to make the image have the size. If the graph represents an image, then that's fine. But it becomes more difficult with general graphs because you need to downsample the graph so that a smaller, coarser version of a graph. So let's say after doing pooling in deep learning, if you do max pooling on a graph, you need to make sure that the resulting output graph actually preserves the geometric structure, some kind of distance between the vertices. And if two vertices are connected in a certain way in a neighborhood in the original graph, after making the graph smaller, after doing pooling, you still want to make sure that it preserves the similar type of connectivity. And I think essentially you want the spectral distribution eigenvalues to be similar as well. So there are a lot of things that need to be considered. But basically, a coarsening graph is that you need to find some kind of, you need to divide the graph into two sets and then assign edges and weights. So it's basically, you do some kind of algorithm to find a bipartite graph. You divide all the vertices into two sets. And then maybe you can take the mean of the connected vertices. So if the graph is bipartite already, this is very easy since an image is bipartite. So you can think of an image, so like you can represent an image using like a checkerboard pattern. So each pixel is either white or black, and you can just remove all black pixels, for example. So that's already bipartite. But for graphs that are not bipartite, it's more difficult. You need to have some kind of other criterion. Maybe you can calculate a normalized cut, which is a way of defining a good way to split the graph into two parts while still preserving some properties. So I just want to mention quickly about wavelets also on graphs, what you can do with that. So I'm not sure if you know what wavelets are, but in computer vision, before deep learning became quite popular, wavelets were very popular for denoising or calculating features. So I would say deep learning is sort of an extension of wavelets, because previously you had handcrafted wavelets that were very mathematically beautiful and had nice properties, and then you can use them by doing convolutions, for example, to analyze a certain type of frequency or properties in your image, for example. But then deep learning came, and now it's just, we learn that from data, so the math is gone. But like in classical signal processing, you usually define a wavelet by defining some kind of function, such as that's called the Modern wavelet. So this Mexican hat wavelet is like an interesting textbook example because it looks like this sombrero that like some Mexican people have maybe. The details are not important about this function, but it looks a bit like this. And you do a convolution of this wavelet with a signal. And it will capture some kind of edges, for example, in the image. But starting from the modern wavelet, you create child wavelets at different scales by you do scaling, as I talked about before, this dilation operator, and you also translate the wavelet to different parts in the image. So this will give you different information about the image. So, for example, if you have very sharp edges or more like larger, more global properties. So the good thing about wavelets is that unlike the Fourier transform, the wavelets are able to localize a signal both in time and frequency. So if you do the Fourier transform or the graph Fourier transform, you will know that somewhere in this graph or image, you have a high frequency component, but you don't really know where in the graph or image it exists. But if you use wavelets, you can know that, oh, okay, so in the bottom left corner, you actually have a lot of edges, but in the top part of the image, you have more like smooth area. It gives you more detailed information about the signal. So so wavelets are actually possible on graphs as well. So one example how to do this is in the graph spectral domain. This is called the spectral graph wavelet transform. So maybe the details are not so important, but basically you have a set of different wavelets. One scaling function that captures all of the average signal properties of the graph signal. And then you have k different wavelets that capture different types of frequencies. So you have one wavelet that's designed to capture very fine edges, on the one that captures more long-range discontinuities. So this is very useful for analyzing whatever properties the signal has that's defined on this graph. The way that you do it is that you use the graph replacement matrix, and basically this notation means here that you multiply the eigenvalues of the graph replacement matrix by this filter H hat, and then you translate it to somewhere by using this delta signal, which I talked about previously. You need to translate signals in graph signal processing using a delta function because translation is not defined in the vertex domain. The wavelets are defined in a similar way. Basically, it's not important to talk about details. But basically, so what you get is that once you calculate these wavelets, I won't talk about the details, but you will get a resulting matrix. And this matrix psi here is, you can just multiply it by this vector that represented your graph signal, and you will get an output matrix that contains information about how much of the like high frequency signal do we have in this beginning of the graph or around this vertex here. So basically, you can get information about the graph signal in similar ways that you can do in classical signal processing. So this is very useful. So here's an example. So please ignore this CKWT. I didn't talk about that. But so we have this Minnesota state graph again that represents the traffic flow. So if we define a graph signal on it so that the red color here represents high values and blue represent the negative values. So you can see that there's some kind of smooth area of the signal around the west side of the state. But once you go to the east, there's a sudden, like an abrupt discontinuity, a drop in a graph. So basically what this spectral graph file transform does is that it allows you to look at the average values using the scaling component. So you know that on average, in a local area, the signal looks like this. But if you use the wavelets of this transform, you can also know where this discontinuity happens, and it will discover that it's around these borders of this graph, and it will also give some information about what characteristics, what frequency type this discontinuity has. So this example is useful because it's sort of a visual, so you can sort of relate to it. It's almost like an image. But basically, this applies to any type of graph. So if you have some kind of graph that describes a sensor network, you can still understand where you have discontinuities in a graph or something abnormal is happening. So finally, I will just talk about some applications. So it goes without saying that deep learning is very popular, right? But what we apply deep learning to is mostly tasks that are Euclidean, or at least the way that we apply deep learning is Euclidean. So we assume that we can represent the signal as a vector, and in this, well, each feature point is related to another feature point by some kind of Euclidean distance. So dimensionality reduction is another classic machine learning task that we usually do by just representing the signal as a vector and then produce it. But this can also be done for graph structure data by using graph signal processing. So I'll just briefly mention how we can generalize these methods. So one is the graph CNN, which I have an implementation of on our GitHub. So basically, this is a normal CNN, but the interesting thing that instead of inputting a tensor or just an image, you can input any arbitrary undirected graph that has a signal on it. So instead of inputting an image to the graph CNN, you input a graph that represents something. So this graph can be a social or biological kind of telecommunication graph. And then you learn these spectral filters, which are essentially learning convolutions, as I said before. So it will do a convolution with respect to the graph structure, and you can apply a ReLU activation, and then do graph coarsening, which corresponds to basically classical pooling in deep learning. And it will create a more coarser version of the graph that hopefully represents some similar properties of the graph, and then do another convolution, and so on in a standard CNN type of manner. So finally, you can also apply fully connected layers if you just want to completely ignore the graph structure. So an interesting connection here is that I think classical deep learning is basically a graph CNN which has no edges at all. It's just a graph where each vertex is not connected to anything else. That is for the fully connected layers. But a graph CNN is more general, and you can apply it to take advantage of the structure that your graph has. Another thing you can do with graphs is PCA. So I'm not sure, probably you know PCA, principal component analysis. So usually you can describe PCA as an optimization problem. You have some kind of feature matrix X. That's your data set. And using this, you want to learn some kind of low rank matrix U that has lower dimension, but still represents the same feature vectors in some way. So what they did in this paper is that they added 2 extra regularization terms to this problem, which I will not talk about the details, but basically what they do is that these regularizers depend on the graph structure. One is called graph total variation, and the Tikhonov graph regularizer. So what the graph total variation regularization does is that it encodes some kind of regularization that the graph signal should be piecewise constant between different samples. So, for example, if you have an image and you represent each pixel as a vertex, so each vertex is a sample, then usually in the image you have piecewise constantness between pixels. So if it's approximately constant at least. So if an image in a pixel has a certain value here, then if you just look at neighboring pixels, it's usually quite similar. Like the skin color here is quite similar to the skin color here, and so on. That's usually true for images. The other Ticonon graph digressor encodes an assumption that the signal defined on each vertex, there should be some kind of smoothness between the features with respect to some graph structure. So we will learn a much more lower dimensional feature representation that still represents whatever graph structure you had from the beginning. So maybe it could be like if your feature is well, so in NLP you have the word to back embedding, right? So maybe there is some assumption that certain parts of the feature vector should be closer than another ones. And this type of graph piece is able to encode this information. And finally, I want to add some applications in computer vision and graphics, which is mainly my interest. Why I'm sort of interested in combining graph signal processing and computer vision. Those are more like main research interests. So thanks to, for example, the Kinect camera. So recently there's a quite big increase in using computer vision that works on 3D geometric data, because you can easily get a point cloud that describes the geometry of an object. But so even though like using that camera, we can get a point cloud that describes objects, most approaches are just tried as they are, or we force them to be. We force these. We force the point cloud to be represented as an image or something that's Euclidean. So this has some problems. So, like the topological structure may be broken. You have details that are lost. If you think about recording a human body using like a 3D camera, if you convert this to an image, you can only represent what actually is seen by the camera from the forward direction, but actually what's ever behind, like on the back, you can never represent both what's in front and the back of me by just using an image. But on the other hand, if you would represent this as a graph, you could actually keep track of what's behind or what's occluded, for example. And another drawback of using Euclidean structures here is that the representation itself is not quite intrinsic. So if I want to represent how a human body looks, and then I just rotate a little bit to the right, like my body is still the same, but as an image, the pixels change quite a lot, so the representation is not invariant to whatever geometric object you're modeling. On the other hand, if you represent the body as a graph, the graph itself has no concept of rotation. So if you create a graph that represents me from the front view or this like side view, the concept of rotation does not exist for a graph. So it would still be able to model the body in the same way. So there was one paper here by Boscaini et al. In NIPS also this year. They developed a method that's called intrinsic deep neural networks, which represents a graphical object as a graph, and then learns convolutions that are, well, they sort of encode this invariance to the formations in the model. So this really reduces the number of degrees of freedoms that our machine learning model actually needs to learn. Because like a normal CNN that's applied on images, it needs to learn from data to be sort of invariant or robust against occlusions or rotations, for example. But if you already represent the image as a graph, or not image, but the actual object as a graph, then this assumption of rotation invariance is already built into the graph itself. So the whole problem becomes much more easier to learn. So what they did is that they solved this multinomial logistic regression problem. So I'll just basically describe the problem itself. So given different body types that look quite different in image domains, they just want to learn some kind of correspondence function, u theta, that is able to understand if this point x here on this body corresponds to the same part of the body on another type of them. So in the method, they show that this is possible. So, and it works much better than just using raw images. And finally, I will just mention something I did during my PhD. So my PhD research here in Japan was also related to this topic, basically. So I explored how we can combine graph signal processing for the task of 3D human action recognition. We developed a method where we represent an action as a time series of graphs. So the idea is that if you represent the human body as a skeleton structure, this you don't need to learn how well the rotation invariance anymore, because the graph, when you have constructed a graph, you can rotate it as you want. So we show that this works really well for cross-view action recognition, where you record an action sequence from different angles. So like the action performed is the same, it's just that the camera angle is different. So on the image space, it looks quite different, but as a graph, it looks very similar, so it works very well. And I should quit soon, I guess. So finally, I'll mention some problems. So one problem in this field is that the graph rotation matrix really needs to be fixed in order to graph signal processing to make sense, since it's based on the eigenvectors of this matrix. And if you just add or remove one edge in the graph, the eigenvectors change quite drastically. So you can no longer compare the graphs. That's a big issue. So we need to find out how to generalize a signal learned or some filters learned on one graph, how this will, what it actually means if we do it on another type of graph. And another thing is that we haven't found any fast graph Fourier transform yet. In the classical signal processing, Fourier transform is very efficient, it's n log n. But for graph signal processing, you need to still calculate the eigenvectors of the graph rotation matrix, so this is quite costly. And another thing is that when you want to generalize deep learning to graphs, we have some papers recently, but it sort of includes some kind of handcrafted parts, because the graph is designed by the humans and the graph describes the problem. If you make a wrong choice in how you design a graph, then it heavily affects the results. So and another issue is computational efficiency, because most GPUs, they are designed for assuming that we have a Euclidean structure and we have a tensor. But if you have graph structure data, you don't usually have some kind of grid structure to it. So how can we achieve efficient computations? This is another issue we need to explore. So finally, but yes, basically, like the purpose of this talk was not to make you experts of graph signal processing or anything like that, but I just wanted to give you a lot of different examples of what can be done or what can be not done, what kind of problems do we have in graph signal processing. So in order to maybe, if you find this interesting, we can discuss more and read more papers for the actual details. But basically what you want to remember is that graph signal processing, it depends on a graph rotation matrix. That's very central, and you use the eigenvalues of this matrix as a frequency interpretation. You have some generalized operators, you can do filtering and convolution. And these methods are very good at capturing structural properties of the data. So yeah, and some applications, you can represent images, videos as a graph. You can represent the temporal evolution of something as a graph. And recently I've seen that deep learning on graphs is starting to become more prevalent. There are several papers in NIPS this year. So there are a lot of interesting ideas to do, and you can also create some robust methods by denoising signals that are defined on graphs. And it's like the area itself is quite unexplored. It's not really ready for products or performance yet, but there's a lot of theoretical things that we need to find out. So it's an interesting, rather unexplored area so far. Okay, so some references, and thank you for listening. So if you have any questions, then go ahead. Yes.
So I think the graph construction itself is a very requiring some domain-specific knowledge. And how do you think can we generate such a graph structures from some raw data automatically using?
Yes. So there are actually some papers that try to encode certain assumptions. They have a prior that the signal should be smooth between vertices, and based on this assumption, they learn the structure from data. But the problem is that maybe you will create a graph representation that only includes the smooth properties of the signal and doesn't capture more high frequency properties. I'm not sure, but there are some attempts at that, but it's not very popular yet. If we could use deep learning maybe to learn the structure and the signal in the convolution of vectors itself, that would be very amazing. Any more questions? Yes.
How can we measure similarities between two graphs in this space and this space?
You mean if the actual structure of the graph is different?
Yeah, I have said you have said after Fourier transformation, we can convert some graphs here in this space. So I'm interested in how can we define the similarities in this space and this space? Do you have any comments on how this?
So this framework I presented today, it assumes that the structure is fixed. So what similarities you can measure are vertex similarities. But if the actual structure is different, then this framework doesn't tackle that yet. But there are some other methods like graph kernels that actually compare the actual structure of the graphs. We cannot compare the similarities yet, at least. That's actually an open problem, which is important to solve. Yes? Yeah, you could create new edges, but the problem is where to put them, I guess. I mean, this becomes quite application specifics for the human body. As you said, it's quite easy. So the new vertex between my hand and elbow is probably somewhere in between. But for a more general graph, it's not easy to understand ways. Yes. Right. So that's one of the big problems now, that the graph needs to be handcrafted. There's some issue that we discussed that you can learn the graph structure, but so what you can do, of course, is that you could do downsampling and then just remember whatever correspondence you had between vertices and then do upsampling again. But you can never upsample it more than the original graph, unless you actually have some domain-specific knowledge about what this new vertex or edge should represent. So it's still an open research problem. Any more questions? Okay. If no more questions, then thank you very much.